Hello, folks. Today we're going to do probably the first truly new thing for physics that we've talked about so far. So far, everything that we've done has been review of stuff you would have done last year. Maybe some more complicated problems, but the topics and how to do stuff was pretty much review. Okay. So today we're going to have today in the next video we're going to have some new stuff, and that involves the derivative. Now, this is actually something that you would do in calculus, and those of you that have already had calculus, this is going to be really easy for you. Those of you that have not or are taking calculus now, you probably haven't gotten to this yet, and that's okay. The stuff I'm going to show you is just the stuff you need for this class, and it's actually relatively simple. Okay. So in previous talks, we've talked about graphing motion, and particularly, let's say we draw a position time graph. Okay, so position time. And let's say it's like this. Okay. Now, if I asked you to figure out a velocity, you know that velocity on a position time graph is slope. Now, there are two different velocities I could ask you for. The first one would be, if I would say I gave you 2 points on this graph, let's say those 2 points right there, and I said, determine the average velocity between those 2 points. Well, the definition of average velocity is change in x over time, okay? So what you would do is you would have the two x values there, and you would subtract them, get your delta x. And then you'd have your two time values there, and you'd subtract those to get your time, and that would be your average velocity. In other words, imagine you drew a straight line between the 2 points. You're finding the slope of that straight line, and that would be the average velocity between those two times. Okay, so that's relatively easy. Okay. However, what if I asked you for this point right there on the graph, the green dot, what if I asked you for the velocity at that moment, at that time? Okay. Well, last year for graphing, what they would have told you was to draw a tangent line. Okay, and that tangent line, it touches the graph at that one point and is parallel to the graph at that point. Okay. And then you would pick 2 points on that green line and you would find the slope, and that would be an estimate of your what we call instantaneous velocity at that time. Now, it wouldn't be perfect because we're drawing a tangent line by eyeball, and we'd all probably have slightly different values for that. Okay. But it turns out that if you know the function of x versus t, if you know the equation for that graph, it turns out that you can determine the exact slope at that time. In other words, on this graph, that would be the exact velocity at that time. Now, in order to do that, you need to be able to write the graph as a function. Okay, so I'm going to back up a little bit here, and we're going to talk about graphing in general. And this is something that you would have probably done in pre-calculus. Okay, so in this case, I'm going to draw a graph of y versus x. So that's more generic, and I'm going to draw that same shape again, a curve. Okay, and let's assume that we can write y as a function of x. Okay. And as a matter of fact, I'm going to do an example in a minute where we're going to write this way. We're going to pretend that y equals 3x squared. So it's going to be a quadratic. Okay. And what I want to do is I want to find the slope of that graph right at our green dot there. Okay. So what they would have had you do last year in pre-calculus, or for some of you a couple of years ago, is you would have picked that point. We'll call that x comma y. And then you would have picked another point. Now, I might be labeling these slightly different than your teacher may have, but it's the same idea. And then this would have been, they would have told you to call this distance along the x-axis, they would have told you to call that h, okay? So this would be x plus h, and then we'll just call this y final, okay? And they would have said, okay, start by using those things, find the slope between those 2 points, okay? So slope is rise over run. Now, you guys know that is y final minus y naught, or y2 minus y1 over x2 minus x1. Okay, but really, it's the function of x final minus the function of x naught over x final minus x naught. Okay, and for some of you, you might be starting to recognize this. So I'm going to go ahead and plug in for this example, okay, instead of x final, I'm going to plug in x plus h. So slope is the function of x plus h minus the function, and instead of saying x naught, I'll just say x now. I'm just going to replace the x naughts with x. And then divided by x plus h, that's your x final, and then x naught, we'll just call that x, okay? And this, your teacher would have called the difference quotient, okay? And we're going to use that to find the slope of the graph at this one point, okay? So for our example here, first of all, look at the denominator. You'll notice that you got x plus h minus x, so the x's cancel. All right, you're just going to have an h in the denominator. In the numerator, we're going to actually try this out. So I'm going to try this out with my function, 3x squared, just as an example. So we are going to plug in x plus h in for 3x squared. So I've got 3 times x plus h quantity squared, okay? Minus, now it's going to plug in x into 3x squared. You get 3x squared, okay? All over, we said x plus h minus x is just h, okay? Now I got to do a little math here, so I have to FOIL this left-hand term out and multiply everything by 3. If you do that, you're going to have 3x squared plus 6x h plus 3h squared, and you have your minus 3x squared sitting there, and then all over h, okay? Now, thankfully, our x squared terms drop out. They cancel out, and you have the slope equals 6x h plus 3h squared over h, okay? Now, going up here to the graph, I want to know the slope at that point. So what do I want to do to h? Well, I want to make h as small as possible. I want to make h really, 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 really tiny, okay? So what we're going to do is we're going to have h approach 0. It's not going to be 0, but it's going to be really, really, really close to 0, okay? Now, if you look at the numerator, you have 2 terms up there, okay? If h is way, 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 way smaller than x, then this first term is going to be way, 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 way bigger than the second term, orders of magnitude bigger. So what we can do is we can get rid of the second term. It's really close to 0. It's you know, a really tiny number squared, okay? So your slope approaches 6xh over h, which reduces down to 6 times x, okay? Now, it turns out that that is the exact slope at any point. So for instance, if this value here, if this x value was 2, let's say, okay, then your slope at that moment would be 6 times 2. Your slope would be 12. So this slope right here would be exactly 12, okay? So that's called the difference quotient. Now, I'm going to write the original function again, y equals 3x squared. And I'm going to write this. This is the slope, and that equals 6x. All right. Hopefully, if you look at those two things, you might see a pattern, okay? If you take 3 times 2, you get 6. And then if you take 2 minus 1, you get the new exponent of 1. So we call this the polynomial rule, okay? Now, before I do that, I want to mention something, the slope. Okay, here's how we write that in calculus. We write it as dy over dx. Now, what you guys are probably used to is delta y over delta x, you know, y2 minus y1 over x2 minus x1. Well, what we're doing is we're shrinking the deltas down to really tiny values. So when we shrink the deltas down to really tiny values, instead of saying delta, we just say d, okay? So that's the slope. So another way to write this is we say dy dx is equal to 6x, and I'll put the 1 there, 6x to the first, okay? All right, so let's kind of recap here and come up with a general rule. If you can write your equation as a polynomial, so if y is a function of x such that y equals some constant times x to some power. That's a polynomial, okay? Then dy dx is equal to the coefficient out front becomes c times n, okay? You multiplied, in our example, we multiplied the 3 times the 2, we got a 6, okay? And you have x, and then how do we get the new exponent? Well, we subtracted 1, so this becomes n minus 1, okay? All right, so we're going to try this out very briefly on 2 examples. The first example, let's say I write a polynomial. It looks like this: 3x cubed plus 7x squared minus 2x plus 8. Okay, what is dy dx? What is the slope as a function of x anywhere along that curve? Okay. So you're just going to do the polynomial rule, and you're going to repeat it. So the first term, you take the coefficient times the exponent, and you get a 9. And you have x, and then 3 minus 1 is 2. Okay. The second term, you take 7 times 2 is 14, and then x, and then 2 minus 1 is 1. Now, do you have to write the 1 there? No. Okay, but I'll just write it there as to keep track of it. Now, this next term, it says 2x to the, it's to the first, even though it's not written there. Okay. So we got a minus, here's our minus. 2 times 1 is 2. And then you're going to have x to the 1 minus 1. Well, that's 0, x to the 0. What's any number to the 0 power? Well, it's 1. So I'll put the 1 here, but you don't need to do that. Okay, so it's just x to the 0. Plus, now this last term, it's 8, and then it's x to the 0. Okay, so what's 0 times 8? Well, 0. Okay, so if I were to write this a little cleaner, you're going to have dy dx equals 9x squared plus 14x minus 2. So what you've just determined is the slope of that graph at any position. Any x you put in there will tell you the slope of that graph at that moment. Okay. Now, I'm going to do one more example with you. We have equations of motion. So for instance, we have x equals x naught plus v naught t plus 1/2 at squared. Well, what we're going to do in this case is we're going to take dx dt, okay, the derivative of this, okay. The first thing is a constant. It's not a function of t. So just like up here, what was the derivative of any constant, okay, the derivative of any constant is 0. So you got a 0 plus a constant times t becomes just a constant. So that was like, in this example up here, that was like the 2x became a 2, okay? And then plus, you got 1/2 at squared. So I take the 1/2 times the 2, and I get a 1. I still have the a sitting there. And then t to the 2 minus 1 is t. So what is this? Well, this is velocity. V equals v naught plus at. So the derivative of position is velocity, okay? And then finally, I'm going to do a derivative of that, dv dt, okay? The derivative of a constant is 0, okay? Plus, you have a times t to the first, which becomes a times t to the 0, or just a. So that's the acceleration, and these are constant acceleration questions. So your acceleration is a constant. It's not a function of time. If I were to graph velocity versus time, it would be a straight line. The slope of that line would be constant. It would be a, okay? All right, the next video, I do have a more involved example, but I wanted to show you that first. So the key on this is, for our purposes, we're going to be using this polynomial rule quite often for a lot of the problems we're going to do at the last part of our unit. Hope that was helpful, and thank you very much.